Okay, this is the next section, section 4 of chapter 1. We're going to build functions from other functions. We'll combine them algebraically, we'll do compositions, and we'll talk briefly about relations of implicitly defined functions. And the reason why is most of the functions that we're going to have in this class are really just combinations of other functions. And it's really good to see that connection because you'll see, you understand some of the basic functions and their properties, so when you see the more complicated ones, you can see that they're just combinations of the easier ones that you're already comfortable with. So you need to know some things first of all, some notation. We're going to use this for sum, so when we're adding two functions together, we're just going to use this notation right here. Just means add two functions, as you'll see in the next example. Same thing with difference, just f minus g of x means take the difference of the two functions, subtract them. Product, same thing, means just multiply the two functions. Quotient means just divide the two functions. And keep in mind, you can't have a 0 in the denominator because that'd be undefined. All right, so here's an example then. Super simple. When you add them, you just add them. So the notation would be f of g of x equals x cubed plus the square root of x plus 1. Okay, when you subtract them, the notation would be f minus g, so x cubed minus the square root of x plus 1. And when you multiply them, the notation would be f times g of x equals x cubed times the square root of x plus 1. And there's nothing to even simplify in any of these, so I'm just leaving it like it is. And then f divided by g of x equals x cubed over the square root of x plus 1. Now, you would have to put some restrictions on these domains, obviously. Like, for example, the bottom one, x cannot be negative 1. And also, the bottom, this x plus 1 has to be greater than or equal to 0, so you don't have negatives underneath the radicals. So we can talk about domains, and we will a lot in the homework help video and in class. So we're going to have to talk a lot about domains because this can be really tricky to figure out the domain of a composite function. So let's look at composite functions then. F of g of x, you can write it like this or like this. So this means f of g of x. This means f of g of x. Now, we're going to talk about this as we do problems that'll make more sense, but what you do is you take x, you plug it into g, and you plug that into f. So you work inside out. Basically what you're doing is you're evaluating the function f of the function g of x. So here's like a diagram what it would look like. G of f of x is really just you taking x, you evaluating g, the function g, and then plugging that into function f. All right, so here's an example. If I want to do f of g of x, I take g of x right here, and I plug it right in for f. So I plug it right in there. So it'd be, this would be 2 raised to the square root of x plus 1. Okay, now if I want to do the other way around, so now I want to take g of f of x, I take f of x and plug it into g. So now I'll take f of x and plug it into g, so in for that x right there. So it'd be 2 to the x plus 1 square rooted. All right. So we'll do a lot of examples like that in the homework help, and hopefully this will start to make sense. But let's look at decomposing. This is a tricky one, but let's find f and g, two functions, such that the third function, h of x, is really just the composition of those two. So basically, figure out what f and g are that would make this function right here, if we were to compose them. So we're going the other way around now. There might be different answers for this one, but let's do g of x is equal to x squared plus 5. And then that would make f of x equal to the square root of x. So that if you do this composition, if you took g and plugged it in, you'd get this function here. Now, there probably are different answers, like what if I just called g of x, x, and then I called f of x the square root of x squared plus 5. So, I realize this is pretty simple. This answer is better. But this would also work, technically, because if you take g of x and plug it in, you do get h of x. So, different answers, but I like this one. Okay, next is implicitly defined functions. Sometimes we're going to have these things that aren't really functions, and we're going to call them relations. So, like, for example, if we have, the positive and negative branches of a parabola like we have here, then it's not a function. It doesn't pass the vertical line test. When you plug in one x value, you get two different y values. So we're going to call that a relation instead. It still gives us something useful that we can talk about, but it's not technically a function. All right, so let's take a look at one of those examples right here. Now, in Desmos, you can graph this right away just by plugging it in. Let me show you that. So that's nice. Desmos, you can plug right in and it'll just graph the relation for you. Not a function because it doesn't pass the vertical line test. We know it's an ellipse, so that's helpful. But if we're going to graph it in our TI-84, our TI-84 only graphs if we solve for y. So, you know, if you ever find yourself in a situation like a standardized test or placement test where you have just a graphing calculator, you need to solve this for y. So to do that, we have 4y squared. We're going to subtract the other terms to the other side. So that gives negative 9x squared plus 24y. I'm going to divide by 4. And then I'm going to square root. So it'll be y equals, now we have this plus or minus thing going on here, where we have negative 9x squared over 4 plus 6y. Now, the positive answer will give you like, you know, this part of it, and the negative answer will give you like this part of it or something. So, you know, our calculator will graph it if we solve for y, and we can describe this then as an ellipse, and Desmos helps a lot. This is an ellipse centered at 0, 3. You know, the major axis has length 6, the minor axis has length 4, things like that. And later in the year when we study conic sections, we'll take this and we'll put it in standard form for a conic section where we can find that information in a different way without the help of Desmos or our graphing calculator. All right, I hope this helps.